So, welcome to this class on hardware security. So, we have been studying about side channel attacks, and in particular we have been discussing about power attacks. So, in today's class we shall be trying to see a new form of side channel analysis, which is called as fault attacks or fault analysis. We shall start with trying to understand what is the relationship between faults and information leakage. I will be discussing about a classic fault attack on the RSA crypto system, and then we shall be trying to look into how to perform a particular type of fault attack, which is called as differential fault attack, which is basically a combination of fault attacks with differential cryptanalysis, and try to apply it on AES. And then we shall be trying to look into DFA on AES, targeting specifically the 8th round input of AES 128. So first of all, what has got faults to do with information leakage? So let us try with a very high level description of this with a very like an example, very simple example. So imagine that there is a dealer Jack. So this particular example has been taken from the Sorcerer's Apprentice Guide to Fault Attacks, which was shown in FDTC 2006, which is a workshop on fault attacks co-held with chess. And this particular example shows that there is a dealer Jack who is a supplier of cards and planes and wants to essentially sell it to a customer who is called, say, Dino. So the idea is that you can see that these are toy cards and toy planes. So therefore each card costs around $3, and suppose each plane costs around $5. So Jack asks Dino, how will you pay? So Dino says that he will send $15 by postal order, and immediately you can understand that there are two possible transactions. One, it can be that there are 5 cards which are being procured, or it can be that there are 3 planes which are being procured. So the question is, right, essentially it can be any of these transactions, and of course, like there is a malicious, imagine that there is a malicious postman who is curious to know which of these transactions has taken place. So information theoretically, it means that there is a 1 bit of uncertainty. I want to know whether it is transaction 0 or transaction 1. So therefore, right, meanwhile Jack prepares the package, okay, and sends it or prepares it to courier it to the customer Dino, and therefore, right, it gives it to the postman. Now this postman is malicious and curious, so therefore, right, he does this. So he basically kind of applies a fault or kicks it strong enough to break exactly one toy in the parcel. Okay. So the fact that like he is able to break one toy can be called what is called as fault controllability. Okay. So suppose he controls a fault so that only one single toy has been broken. So therefore, right, when he gives it to Dino, and imagine that suppose there has been, of course, like like that when we do online transactions, it is kind of assumed that if there is a broken item which is received to us, then we do not pay for it. Okay. So therefore, based upon that, right, of course you can understand, since one of the toys has been broken, therefore Dino either pays $12 or $10. Okay. And therefore the moment the postman is able to see like which kind of payment the customer does, he is able to understand which of these two transactions took place. Okay. So this is a very simple example, but kind of shows us that faults essentially can be used to extract secrets. Okay. And this has been a widely researched topic, and there has been several attacks which people have developed on crypto systems. In particular, right, the fact that one can easily, or like I would say, because of the development of fault injection techniques, and the fact that you can actually inject faults with very high preciseness and also at low cost, has given more impetus to this discourse. So hardware faults can have various sources. For example, it can be induced by voltage glitches, by light beams, by laser beams, and so on, and many other ways. Okay, and you can probably envisage that if the system gets more and more complex, then the chances of having faults is also increased. Okay, and what we are studying here is that fault tolerance is extremely important in the context of cryptography, because not only the fact that you do a faulty execution, but you also divulge your secret key. Okay, and therefore it is of paramount importance. So let us try to relook or look back at the RSA crypto system, particularly in the context of faults. Okay. So, imagine that there is a decryption, and you know that in public key cryptography, when we do decryption, we use the secret key. So, imagine that there is an attack, there is a kind of crypto system which is doing decryption, and this is essentially subjected to a fault attack. So, the attacker, of course, like in this kind of attacks, we have to state something which is called as a fault model, which basically states what is the power of the adversary. So, here we assume, for example, that the attacker can flip a single bit in key D, okay, and based upon this assumption, what happens is as follows. So, therefore, imagine that the cipher that is obtained by encrypting a message M using RSA is, say, S. Okay, that means I am using, I am basically doing a simple encryption using RSA, and it works as follows. We basically take, for example, the message M. The message M is your message, and you perform an encryption. So, that is power of E, and you do a modulo with a public component N, and you obtain the cipher which is denoted as S. Okay. So, this is equivalent to saying that I take S and I raise it to a secret D, and I do a modulo N, okay, and I get back the original message M. So, now imagine that there is like a crypto system which is doing this operation, and there is a secret exponent inside it. Okay. Suppose imagine it is a hardware device, and it is doing this computation, that is S power of D modulo N to get you the plain text. Okay. So, now the attacker injects a fault, and imagine that it is able to create a fault in the ith bit. Okay. And therefore, right, because of the fault, it gets a faulty decryption done. Okay. So, imagine that in one case it gets a correct decryption done, in another operation it gets a faulty operation out. Okay. So, you can actually write pretty much this D as a binary exponent, for example, from D n minus 1 to say D 0, where your ith bit is denoted as Di. Okay. Imagine that this fault is able to flip Di. Okay. So, you can say that like how can I flip Di? So, like in reality actually there may be several ways in which I can flip a particular bit. Okay. For example, like when there is a circuit which is in operation, I can take, for example, and I can suddenly make a voltage fluctuation, or I can suddenly change the clock of my supply. Okay. I can probably take an electromagnetic gun and shoot, and that can lead to perturbations which can flip like randomly bits. Okay. And there is a probability, and actually it can be a significant probability that a single bit gets changed, okay, or flipped. So, there can be various ways of doing that, and right now we are assuming that suppose like somebody is able to make a flip in this way. So, what is the ramification of that? What is the implication of that on security of say RSA kind of algorithm? Okay. So, we know that if this is happens, then if we just look and kind of elaborate this operation, right, you can easily observe that what we are basically doing is this. We are getting M, and M is S power of, we know that this is nothing but Dn minus 1 till D0. Okay. So, therefore, this is written in binary format, and that is equal to nothing but S to the power of 2 power of n minus 1 Dn minus 1 plus 2 to the power of I Di, okay, plus D0. Okay. And now imagine that somebody is able to flip this Di, and therefore, Di becomes Di hat because of the flip. So, Di becomes say Di hat, it gets complemented, a 0 becomes 1 or a 1 becomes 0, and therefore, right, rather than getting M, the attacker essentially gets S, which is or gets M hat, which is nothing but S to the power of 2 to the power of n minus 1 Dn minus 1. So, everything remains same except the ith bit becomes Di hat or Di complement plus so on till D0. Okay. So, therefore, now if I take a ratio between them, that means I take a ratio of M and M hat, then everything cancels out except we get 2 to the power of I, and I get Di minus Di bar. Okay. So, what does that imply? So, that is essentially written over here, and so what is written over here is just a reciprocal of that, that is M hat by M is S to the power of 2 to the power of I into Di minus Di hat, okay, or Di hat minus Di. So, now there can be two possibilities, Di can be either 0 or Di can be either 1. So, note that the attacker can easily compute this part, that is the left hand part. The attacker also knows the value of S because it knows the cipher, and therefore, it can check whether this equation is satisfied or whether this equation is satisfied. Note that if Di is equal to 0, then I get like if di is equal to 0, then that means di hat becomes 1. So, that means, right, if di is equal to 0, you can observe that di hat minus di, okay, is equal to 1 minus 0, which is equal to 1. On the other hand, if di is 1, then this implies that this delta di will be equal to 0 minus, will be equal to 0 minus 1, and therefore will be equal to minus 1. Okay. So, therefore, in one case you will have s to the power of 2 to the power of I, okay, or in another case you will have s to the power of 2 to the power of a whole power of minus 1, that is 1 by s to the power of 2 to the power of I. And since the attacker already knows the left hand side and the right hand side, it can easily check which of these two equations are satisfied, and from there can get the information about whether di was 0 or whether di was 1. Okay. So, imagine that if the attacker is able to do this, right, on every bit, then it can basically on a linear, using a linear time complexity algorithm, can easily retrieve the entire exponent without solving any complicated hard problem. Okay. So, what it shows is that, and you can also imagine that, if even if I assume that the attacker does not know precisely which bit is flipped, right, he can basically very much like make a guess that suppose like the ith bit is guessed, ith bit is flipped, and therefore can check whether which of the solutions give rise to a correct equation, and the probability that you will probably like get the correct value of I also determined is also significantly high using that. Okay. So, therefore, right, basically, right, what it shows, or what this simple exercise shows, is that faults can be quite catastrophic to security. Okay. So, therefore, we need to properly take care of this kind of attack vectors. So, here is a simple exercise or example to show that, and here is like E has been taken as a toy RSA. So, E is 7, N is suppose 7 7, which is like a product of 7 and 11, two prime numbers, and suppose your exponent is D equal to 4 3, okay, and therefore the corresponding key bit sequence is shown here. So, the ciphertext is say 3 7, which is producing M equal to 9 if there is no fault which is injected, and suppose like there is a ith bit which has been flipped and you get 6 7 as your faulty output. So, even if I assume that I do not know the value of I will basically search for a value of I, and I know that I can take any of these 6 possible values, and therefore, I will just keep on guessing, and I will find that for some case, in this case I equal to 3, I will find that this equation is satisfied. Okay. And as this equation is satisfied, this reveals a value that D3 is equal to 1. So, therefore, I can retrieve the value of the secret bit in this manner by just flipping that corresponding bit. Okay. So, this example shows that faults can be applied for cryptographic systems and was essentially the basis of a very seminal paper written by Dan Boneh in 1997, and that has led to a flurry of works on applying fault attacks for various kinds of crypto systems. In particular, we shall be trying to look into a DFA on AES, because AES is, as we know, the worldwide de facto standards on block ciphers. So, here is a quick recapitulation of what our AES does. We have already seen this. In particular, we are talking about AES 128, but that is without loss of generality. It can be pretty much applied to other variants of AES and also other kinds of block ciphers. Of course, you have to like fine tune it to that algorithm. So, therefore, if I take a plain text and if I do an add round key, and then there I do n like 9 rounds pretty much with sub byte, shift rows, mixed columns, and add round key as the round constituents, and then in the final last round I just do a sub byte, shift row, and add round key. I do not do any mixed columns in the final last round. So, if I do this right, I know that, and let us just quickly study about if the effect of error on AES. So, this shows an example where there is a plain text 128 bit and this is the corresponding cipher text. And you see that if there is a single error in the plain text, for example, here it was 2 and I made it 0, this leads to a like a completely random output. You can see this cipher text and this cipher text has got no correlation almost, right, it is kind of completely random. Likewise, if there is single bit error in the key, also that leads to a random cipher text, and therefore, right, it shows that it leads to a completely scrambled output. So, therefore, AES is a like a kind of a wonderful candidate for a pseudo random function in that case. And therefore, we see that like even if there is a small bit error, then there is a wide diffusion in which we obtain in the. So, we get a very nice diffusion and confusion. If there is a flip in the key or the flip in the plain text, then the output is kind of looks quite random. So, in particular, we shall be trying to look on fault attacks on block ciphers just to see so therefore, we are considering the attacks based on induction of faults. Note that faults can be intentional, but can also be accidental. Okay. So, what we are studying is that the fault essentially can actually not only do a faulty computation. So, it is not that you just redo the computation, but it may happen that just because of the fault you have actually leaked your key, and therefore, you actually need to change your key because your key is already compromised. Okay. So, it was first conceived in 1996 by Bonnet, DeMille and Lipton, as I said, by the seminal paper, to show that how faults can be catastrophic on cryptographic protocols. And later on, there was a very nice work by Eli Biham and Adi Shamir to show how differential fault analysis can be performed on DES. And there was a paper in Chess in 2002 to show how optical fault inductions can be performed by a group by Sergei Skorobogatov and Ross Anderson from Cambridge University, to show that faults can be actually inflicted on cryptosystems with a very quite high precision at a reasonable amount of cost using laser beams or using optical techniques. So, let us try to see how differential fault attacks work. So, in differential fault attacks, you have got a plain text, you get a fault free ciphertext, then you basically take the same plain text and you apply the encryption algorithm, and now you basically do a fault induction. So, you get a faulty ciphertext. So, differential fault analysis tries to combine the fault free ciphertext and the faulty ciphertext, and then performs a differential analysis on that. Okay. And that is the basis of what DFA stands for, or differential fault attacks. So, there can be different types of DFA. For example, you can target the data path. For example, you can assume that the fault occurs in the AES data path when we are talking about AES. You can also target the AES key schedule. Okay. For example, you can assume that the fault occurs in the AES key scheduling algorithm, and that also leads to a different variants of fault attacks. You can also, another very important characteristic when you are defining a fault attack is what is your fault model. That means, what is your assumption behind fault attacks. Okay. What kind of faults are you assuming? So, two important kinds of faults is what I have written here, but there can be other different types of fault models. In particular, I have talked about two random fault models. That means, I do not assume what is the value of the fault. I just assume that the fault is localized in a single byte when we are talking about AES. We know that the AES state matrix can be conceptualized as, for example, 16 bytes. I am assuming that a fault is occurring in one of the bytes, and it can take pretty much any random value. Okay. In another case, I will assume later on that suppose the fault spreads across multiple bytes, and therefore, we will talk about that as the multiple byte fault model. So, on the passing, I would like to mention here that there can be other kinds of fault models. For example, there can be a single bit fault model, where I assume, just like as we have seen in the case of RSA, the fault is in one bit. There can also be other kinds of fault models. For example, stuck at 1 or stuck at 0 fault models. That means, I am assuming that the fault is stuck to 1 or 0. There could be other fault models also which can be utilized. For example, I can assume a biased fault model, where I assume that the fault is not random, but is probably biased towards certain values. So, we will see a certain flavor of that in one of the subsequent talks. So, right now here I am assuming random fault models. That means, I am assuming pretty much the fault can take any random value, any arbitrary value. So, therefore, we will be talking about in particularly single byte faults. Okay, that is, attacker is inducing fault at the input of the 8th round in a single byte of AES, and the fault should be non-zero, because if the fault is 0, then there is no fault. So, we will just assume that the fault is non-zero, but it can take any value, it can take any arbitrarily any value. So, I will be relaxing the requirements. So, we will try to relax the requirements made, because that makes the attack more practical, and and fault attacks can be actually practical. For example, what I will be trying to develop is a DFA where there is no knowledge requirement of the fault value, and we will be trying to develop a fault attack which actually requires lesser bytes to be faulty. And in particular, we will try, we will kind of pursue effort to see that whether the fault attack can be done with lesser and lesser number of faulty ciphertexts, so that like a single fault or maybe a double fault is able to retrieve the key or leak the key. Because remember, when you are actually doing an attack on a real life world, you do not exactly have a control on the fault. So, you pretty much try several fault injections, and maybe luckily one of them falls into your desired fault model. Okay. So, therefore, it is important that you develop a DFA which requires lesser number of faults, because then the probability of getting such a fault is enhanced. Okay. So, here is a brief history about how DFA on AES 128 evolved. For example, there was a paper in 2003 in Chess by Piret and their collaborators to do a fault attack with 2 faults for AES with a time complexity of around 2 power of 40. Later on, there was a work which we tried to do on in Africa Crypt, try to do a fault attacks for for unique key with a time complexity of 2 power of 32. We showed that the attack was possible even with one fault, and later on it was further enhanced to do and reduce the key size to only 2 power of 8 values with a time complexity of 2 power of 32, which was further enhanced later on to reduce to 2 power of 30. Okay. So, all these works have been summarized in this journal paper, which is shown or published in Journal of Cryptographic Engineering, published in 2013. So let us try to see the context in which we are discussing the fault attack. So, here you have got an iterated architecture for fault for AES. So, pretty much that means, and it is a very common architecture because it is a very popular architecture where we take AES round. That means the AES round has been implemented on hardware, and we are pretty much iterating the AES round 10 times. Okay. Just keep in mind that the last round does not have a mixed column. So, we have already seen some flavor of such architectures previously. So, now we are considering the clock line, for example, and we are trying to create a setup where suppose I create suddenly a fluctuation in the clock line, where rather than injecting the normal clock input, we suddenly make a inject a fast clock. Okay, and the objective is to create setup time violations in the circuit, which will be manifested as faults. Okay. Now, in other kind of setups, we may probably try to do such a fault injection by attacking the voltage line, where you create a sudden fluctuation on the voltage path. Okay. So, there are practical attacks also which people have mounted by maybe taking electromagnetic guns or maybe laser guns, but without loss of generality, right. Let us assume that is a very simple demonstration or simple scenario where we are trying to kind of inject a fault by creating sudden clock injections in the clock path. Okay. So, now let us try to see how the fault propagates. In particular, just to understand the principle, let us consider AES 128, where the fault has been induced at the input of the 9th round. Okay. So, suppose imagine that the fault takes any random value. So, let us denote it by f, which basically means it is any random value, okay, it is any arbitrary value. So, remember that a byte sub is a bijective mapping, the S box in AES is bijective. So, therefore, it transforms f into some value, say f dash, and then there is a shift row. So, remember that if the fault is in the first row, then there is no effect, and if it is in the other rows, then it just shifts to some other byte location. Okay, but that does not create a problem, because after this, right, the mixed columns comes into play, and if you remember, right, the mixed column matrix, right, then this is how the fault spreads. Okay. So, now you can actually observe this diffusion from information theoretic point of view also. Okay. So, here for example, if I assume that I do not know anything about the value of the fault, then this essentially means that there is still 8 bits of entropy. This byte can take any possible value. Okay. So, now if you consider, if you go ahead, right, like f dash, then essentially there is no drastic reduction of entropy. But if you come to this column, for example, you suddenly see that if I fix the value of f dash, then the entire column gets fixed. Okay. So, now, right, that means that if, for example, if you do not do a fault, right, or do not make any assumption on the fault, then this byte can take any 32 or any 2 power of 32 values, but suddenly now it can, because of the fault, it is constrained and it can take only 2 power of 8 values, which means that there is a reduction in entropy, and that is we will try to develop into a key retrieval process. Okay. So, going ahead, right, this is how the byte sub will basically again convert it into some values like f1, f2, f3, f4, and then, right, because of the shift rows in the last round, you will have f1, f2, f3 and f4. And remember, these are the differentials, because this is the XOR between the correct operation and the faulty operation. Okay. So, now we basically get this value of f1, f2, f3, f4, because we get the ciphertext, we get the faulty ciphertext. If we XOR them, then we get the value of f1, f2, f3 and f4. So, now the question is, with f1, f2, f3, f4, how do you get the 10th round key? So, you can imagine that what we will try to do is we will try to work behind, we will try to work backward. So, what we will try to do is we will basically know that suppose your correct ciphertext is x1 and your faulty ciphertext is x1 plus f1, remember that the differential is f1. So, we will make a guess for the corresponding key. The key in one case is k1 and in the other case is also k1, because you are operating on the same key in both the correct ciphertext and the faulty ciphertext. So, now we take an ISB. So, ISB stands for the inverse S box. So, we also denote it by S inverse. Okay. So, that means, right, if I basically just do this, that is I take the inverse of x1. So, basically I have got two operations in parallel. So, I get x1, which is my correct cipher, and I get another operation where I get x1 plus f1 because of the fault. So, here there is a fault, right, I get x1 plus f1. So, now what I do is I know that before this there is an XOR, that means I am just concentrating right now on one byte of the key. Okay. So, that is again like you are doing the attack part by part. So, imagine that here K1 is a corresponding key and this is also again K1. So, therefore, right, I just take an XOR between them to come to these locations. Okay. So, remember in the last round before this you have got an S box, because you have got an S box here, you have got an S box here. Okay. So, if you want to go behind this, right, if you want to go behind this, then you have to take S inverse, you have to take the inverse S box, and that is denoted here as ISB. Okay. So, therefore, if I do this, right, I will probably come to a specific state matrix location. I will come to I will come to the differential here, okay, and then I will try to kind of find out the differential for another byte location, and then I will be trying to use their interrelationships in this equation. Okay. So, therefore, now if you for example go back and just relook at the slide, you will probably see the context. For example, right, if I just work behind and see the relationships, for example, right. So, for example, here you can see that if you observe this particular position, you see that this differential is twice this differential is equal to this differential is thrice this differential. So, therefore, we will work behind like from F1, F2, F3 and F4 and try to use these relationships in my equations. Okay. So, therefore, that is exactly what is done over here, and you can observe that if you do that, right, essentially you see that you basically get that this differential. So, this is the first differential is equal to is equal to double this equation. So, this is equal to double this differential, like this is equal to the same as this differential, and this is equal to thrice this differential. Okay. So, that is exactly what is done over here, and now you basically guess K1, K2, K3, K4. So, you see that K1, K2, K3, K4 has got in the worst case, like generally is got 2 or 2 power of 32 possible values. But now if you just randomly guess a value of K1, okay, so you know that the left hand side for example gets fixed, and therefore the probability that a random choice of K2 will satisfy this equation, remember this is a byte, right, is 1 by 2 power of 8. Okay. And therefore, there are 3 such equations. So, totally right, the probability that a random K1, K2, K3, K4 will satisfy this equation is 1 by 2 to the power of 8 whole power of 3, that is 1 by 2 power of 24. Okay. So, therefore, right, on the expected number of possible key K1 quartets like K1, K2, K3 which will satisfy this equation can be estimated to be 2 power of 8. Okay. Therefore, you can pretty much assume that 2 power of 32 K1, K2, K3, K4 values will be now reduced to 2 power of 8 values. Okay. So, this is the basis of the differential fault attack on AES, okay, and we shall see, like right now we can see that using one such fault you are basically able to reduce the key size to 2 power of 8 values. Okay. So, therefore, right, one important point is that there is no dependency on the fault value because eliminated the fault from the equations, and we are basically like doing this attack with the time complexity of 2 power of 16, because remember K1 there are 2 key bytes which you are guessing in parallel. Okay. So, therefore, the proportionality of the time is with respect to 2 power of is 2 power of 16. Okay. And 1 byte fault reveals 4 key bytes, because you have injected one fault and you have got 4 key bytes, you have got 1 key quartet, but you know that in AES 128 there are 4 key bytes and 4 key quartets. So, therefore, if you want the entire key you need 4 faulty ciphertext if you are injecting the fault at the input of 9th round. But it turns out you can do better by inducing the fault at the input of the 8th round, and that is the sweetest spot so far as AES 128 is concerned. Okay. So, let us try to look at how the fault propagates when you have got AES 128. Okay. So, here is just like a depiction of that pictorially. So, you can see that you have got now the fault at the input of the 8th round, it gets converted to F dash, again like this gets modified because of the 8th round mixed columns, and then you get further F1, F2, F3, F4, and now you come to your like the 9th round shift rows, and therefore, this spreads in this way. You have got F1, F2, F3, F4, and then when you do the mixed columns you get like all these equations. So, that is why now if you target this, then you get all the key values, or you should be at least getting equations which are concerning all the 4 key quartets of AES 128. Okay, and therefore, right, you should be able to get with a single fault, you should be able to get all the you should be able to get in the entire AES 128 key. Remember that I have tacitly assumed this, but I should probably emphasize on this, that is we are trying to get the 10th round of AES, okay, but the key schedule of AES being reversible, if you get the 10th round of AES, you can get the 9th round of AES key, and therefore like you can work behind and you can get the input key, okay. But in a block cipher where the key scheduling is not reversible, you can still adapt this by peeling the rounds. For example, like you get the 10th round and then you basically do a decryption of the last round and you come to the last 9th round cipher, okay, and then try to get the 8th round, okay, in a similar fashion, okay. So you can kind of peel off the rounds, you know, like, and you can still get the input key. It will be more difficult, but still possible. So therefore, right, in this case, when you want to perform this attack on AES 128, remember now we would like to, you know, like exploit these equations. So for example, right now, if I want the, you know, like one key quartet, then I will be targeting these equations like 2F1, F1, F1 and 3F1, okay. And if you want to use this, then you see that when you are working behind, right, you are working behind the S box, which is this. So you are basically going, you know, like this is your S inverse, and you see that here you have got these equations, I mean these bytes involved, A1, A5, A9 and A13, okay. Now because of the shift rows, this gets again located to these positions A1, A5, A9 and A13, okay. So therefore, right, your equations will be concerned with A1, A5, A9 and A13, but remember that the cipher that you have essentially, right, will be so therefore in the cipher bytes, right, you have to basically concern about these cipher byte locations, okay. So this is the 10th round cipher C10 for example, okay. So that is, you know, like so therefore by using this you again derive similar equations, and therefore, right, you should be able to get the corresponding you should get the corresponding or understand the corresponding equations, okay. For example, these are the equations here. So you can see that I have in this equation is involved A1, A5, okay, A9 and A13 as I have just mentioned. Again, you know, like this has got a complexity of 1 by 2 power of 20, I mean probability of 1 by 2 power of 24, a wild guess of the key quartet. So the key quartet here involves these keys like K00, K13, K22 and K31. So these are the 4 key bytes which are involved, and therefore, right, again this reduces to from 2 power of 32 to 2 power of 8 values, okay. Now imagine that you can try to get the equation for the next column and similarly for the 3 other columns, and therefore the entire AES key, right, which essentially had got 2 power of 128 initial values, will now get reduced into 2 power of 8 whole power of 4, which is around 2 power of 32 with one single fault, okay. So now you can actually try this exercise once more. So that means you can again try another faulty ciphertext, and you can again, you know, like take another get another candidate for the AES key, and you take an intersection between them. So you can understand that if you have a reduction from 2 power of 128 to 2 power of 32, that means with something like 2 power of 96 as a probability or as a filter probability, then if you take one more pair, the expected number of key which will survive is expected to be only 1. So therefore, you know, you can pretty much expect that if you take one more fault short or short at the faulty value, then you will probably get a unique value of the key, okay. So that is essentially the crux of how the fault attack works, okay, on AES, and that means that, you know, like 2 faulty ciphertexts will reveal the exact key with a probability of almost 1, okay. So to conclude, faults can be catastrophic for ciphered implementations. DFA works by combining differential cryptanalysis with faults. A random 1 byte fault at the input of 8th round of AES can reduce the key size drastically, and 2 such fault injections can uniquely give the key, okay. Remember that now we have got 2 power of 32 keys which we can get with one single fault, okay. So here are 2 important references which we have followed in this work and in this presentation. Of course, you can always refer to the main textbook, okay. So thank you for your attention.